Okay, so today's speaker is Jeanne Wilson. She got the PhD in Oxford working on SNO in 2004. And then she had two postdoc positions in Sussex and Oxford working on Cobra double beta experiment and then on SNO+. In 2010 became lecturer at Queen Mary and joined the T2K experiment and HyperK2. Since 2019 is lecturer sorry, people are joining at King's College in London, and she's working mainly in SNO+ and T2K and HyperK. Today she will discuss an update on SNO+. So the first slide is already there, so please go ahead. Thank you.
All right, well, thank you very much for the invitation to talk. I'm sorry I can't be there in person, but hopefully if I cut off or something, somebody will tell me and I won't be talking to myself here. So yeah, it's my pleasure to give an update on SNO+ on behalf of the SNO+ collaboration. So just up front, I'd like to introduce the collaboration. It's many institutes, and these slides contain a lot of input from a lot of people. So I'd like to thank everybody up in advance. So what am I going to talk about today? I'm going to start off giving a quick introduction to neutrinos and SNO+, and then I'm going to sort of take a chronological approach and talk through the first phase of SNO+ when we had water in the detector and what we've learned from that phase. And now we're filling Scintillator. We put the scintillator in on top of the water and take the water out the bottom. And I'll talk about what we've learned about the scintillator so far. And then I'll talk about our physics goals for the pure scintillator phase, and then focus on loading with Tellurium, which is our main goal to get to Neutrinos double beta decay measurement with the experiment, and talk about what we aim to do and beyond what we could do after the first stage. So starting off with neutrinos, what do we know about them? Well, we know that they come in three flavors: electron, muon, and tau neutrinos that we observe, but those flavors change as they travel. We see changes between the neutrino flavors, and that's because each of the flavor states is made up of a superposition of three mass states, which you call the mass 1, 2, and 3 states. And these oscillations happen because of the differences between these mass states. So what we measure is the difference in mass, well, the difference squared. And that means that we know these gaps, but we don't actually know the order of them. We don't know which of these three mass states is the lightest. So there's two possible orderings, which we call normal and inverted. And we also don't know the absolute mass. So we don't know what the scale is on this axis. We do know that the neutrinos are much, much lighter than the other fundamental particles, but that's hard to explain if they were Dirac particles like all the other fundamental particles, why their mass is so small. So there's some suggestion that they could be Majorana particles, which essentially act as their own antiparticles, which could explain the very different nature of the neutrino masses. And Neutrinos double beta decay it's a very rare decay. It's a lepton number violating process, and it's considered by some to be the golden channel to probe both the nature and this absolute mass scale of the neutrinos. So this process is only known to occur for 35 isotopes in matter, where they can double beta decay, which means that two neutrons decay to two protons inside the same nucleus, emitting two electrons. And in the case of two neutrino decay, which we do know exists, it would also emit two neutrinos. But what we're interested in is the case where the neutrinos are not emitted from the nucleus, but they mediate the decay, called neutrinoless double beta decay, in which case you just get two electrons emitted and the neutrinos essentially annihilate themselves. And in which case then the signature of this decay, instead of the classic continuous spectrum of beta decay, which you'd also get for double beta decay, will be an excess of events at the very end point for the decay, so the Q value of the decay. And as I say, this will only happen if these neutrinos are Majorana particles, and then the rate of the process will be dependent on the effective mass of the neutrino. So in the case of the simplest scenario, where it's just like Majorana decay mediating the double beta decay, the mass comes into the equation like this. So we have a mass squared term, a matrix element term, and a phase space term, determining the half-life of the decay. And this mass term is actually made up by a sum over the oscillation matrix elements and the individual mass states. And that leads to this plot that some of you might have seen before. It's sometimes called the lobster plot, where you have the lightest neutrino mass on the x-axis and this double beta decay mass that you're probing on the y-axis. And the aim of our game is really to push limits on this mass down as low as we can, to a point where hopefully we're actually detecting the decay, because we're actually seeing inside, seeing the effect of these neutrino masses. So this splitting here is because of the oscillation parameters and these two different orderings. So we sometimes talk about getting into the inverted ordering regime, where we're looking at masses down to tens of millielectron volts, but the normal ordering does suggest even lower masses to probe, which is very challenging. So that's the background. Let's move on to SNO+. So SNO+ is a multi-purpose low background liquid scintillator detector. And as I say, our main goal is the search for neutrinos double beta decay. So our approach is to load a very large amount of Tellurium 130 isotope into our detector, which is basically homogeneous with a very well understood background model. And then we're just looking for this excess of events at that Q value of the double beta decay over our backgrounds. And we want to demonstrate that this process works, that we can control our backgrounds. And if so, then it's potential to scale it just by adding more tellurium into the detector. And once you've made this really low background, well understood detector, you naturally have potential to do lots of other interesting physics. So I'll be talking about some of these as we go along today as well. So this is what the SNO+ detector looks like. It's obviously down underground in SNOLAB, which hopefully you're all familiar with. We inherited this infrastructure from the SNO experiment, but we made various changes to adapt it to hold scintillator instead of heavy water inside this acrylic vessel here. So it'll hold 780 tons of scintillator, and then we'll be loading that with 0.5% by mass of our double beta decay isotope, so tellurium. And we've installed, in order to facilitate that, we've installed a new interface at the top here and a cover gas system to stop backgrounds getting into the scintillator. And we've installed this rope hold down net as well, since the buoyancy of the scintillator is very different from that of tellurium. So the acrylic vessel needs to be supported from above and also to stop it floating away. We still have the water in the external region here, which provides shielding, and 9,300 PMTs to view the events on the inside. So pictorially, I can show you the same thing. So these are the steps we made to move from SNO to SNO+. So there was a lot of cleaning involved. We had to clean off the AV after it had been left empty from the SNO experiment. Here's a picture of the installation of the hold down net, more cleaning. That would be Peter on top of the vessel, I think. We filled with water. We installed cameras into the detector so that we could keep an eye on what's going on inside the detector. So this is an image taken with one of our cameras. We took the opportunity to repair some of the PMTs that had broken during the snow days, and we've installed new calibration systems. And a lot of this work was done by boat as we were filling. So the first phase I want to talk about is the water data. So we actually had the opportunity to take two sets of water data. So the first one was from May 2017 to December that year, and it's about 115 live days, and we've got a number of publications out of that. But what I'll focus on more today is the more recent water data we took from October 2018 till July 2019, which is a bigger data set. It's 190 live days, but it's also got much better control backgrounds that I'll show you. So just briefly, what are the features of a water cherenkov detector? So they detect particles, charged particles, through cherenkov light, and cherenkov light comes out in a forward cone, as shown here, which means that the light impacts on the PMTs in sort of a ring, or actually more of a blob in our case because it's so low number of hits, and we get some directional information on which direction the charged particles were going. So if we have neutrinos coming into the detector, they interact through elastic scattering of the electrons, and the electrons head off in a sort of forward direction, so that gives us directional information. We're working at an energy threshold of a few mega electron volts, and we see roughly 7 PMT hits per MeV. So that's shown here with the N16 calibration source, which is 6 MeV gamma. So we understand this pretty well. So one thing you can do with the water Cherenkov detector is look at solar neutrinos. This is the classic neutrino predicted spectra in flux against the neutrino energy here on a log scale. And you'll see right at the top end, water Cherenkov experiments are really only sensitive to the boron 8 spectra from the sun. So these are the highest energy neutrinos produced. This plot also shows you why you'd want to change your detector to a scintillator detector, because it's got a much lower energy threshold. But we're interested to look at the boron 8 neutrinos because various measurements have been made of solar neutrinos at different energies, as shown by this plot that I took from a recent talk at Neutrino 2020. And at these higher energies, we expect the survival probability of the neutrinos from the sun to turn upwards. But no experiments have actually been able to detect this turn up yet. So that's something, that's a motivation to look for, to check that the models to predict how this flux transitions with energy is correct. Well, not flux, survival probability. So in order to look at these lower energies, we need to reduce our internal backgrounds. And this was one of the things we really achieved in this second phase water data. So we brought the nitrogen 2 cover gas system online, some images of the bags that contain the gas here and a schematic of how it works. And this suppresses the low backgrounds, and it enabled us to go to a much lower threshold for our solar neutrino analysis. On the right, for this low background data, I've got the analysis we performed to extract the uranium and thorium levels in the water. So this was done by looking at events within the water and separating them based on their isotropy into uranium and thorium. So statistically, we can get a very good estimate of the contamination levels of these two naturally occurring radioactive isotopes. And we've got these to be an order of magnitude lower than our previous water data. I can just show you that here. These are numbers we presented at Neutrino 2018, and the solar plot we published in that first water data, where you see this clear elastic scattering peak in the forward direction where cos theta sun is 1. But with the new data, where we've got these much lower background levels, you can see that our peak is, our elastic scattering peak from the solar neutrinos is still there, but the background in the backwards region, which is, you know, less from solar neutrinos and more from internal backgrounds, is virtually non-existent. So that's at the same energy threshold of 5 MeV, and we can push that energy threshold down to 3.5 MeV, and we're still clearly seeing this elastic scattering peak. So we're still seeing our solar neutrinos clearly at this threshold. So we have a new spectrum analysis in progress on this data. So watch this space. Another thing we did with the water data was to look at external backgrounds. These are the components that occur from radioactivity in the components external to the detecting volume, but they're not going to change. When we change from water to a scintillator in this region, they're going to be pretty much the same. So they're going to be the acrylic vessel, the ropes, the PMTs, and the external water. And we wanted to measure these with water in the detector because it's the simplest configuration. We can make use of this directional information from the Cherenkov light. So for the external backgrounds, we did a box analysis. The two parameters here are the radius cubed, which means it should be it's volume normalized, and 1 is the acrylic vessel, and U.R, which gives you directional information. So 1 would be outwards and -1 would be events coming inwards. And then we define in this parameter space boxes for our different components. So the acrylic vessel and the ropes, the external water, the PMTs, and the internal waters on this side. And then we compare this to our Monte Carlo predictions, and we can extract scale factors. So compared to what we put into our Monte Carlo prediction, we actually get smaller factors for most of these components. And summing these up over the relative contributions they make to our double beta analysis, we realize the external backgrounds are currently overestimated in our Monte Carlo by about 20%. So it's good to have these more accurate measurements from in situ. Beyond doing that counting analysis, we can also look at the ropes individually, because if you look at this plot in the top right-hand corner, you'll see the ropes repeat periodically around the detector. every 18 degrees. So if we slice our detector in segments and stack these all up together, we can see the peak in events from the rope regions. And by comparing that data to Monte Carlo, we actually get a very good shape agreement between the two. So we're confident that we're really seeing the backgrounds and the ropes here. Rather than normalizing it to compare the shape, if you do an amplitude from our Monte Carlo prediction, which was based on assays originally before we installed things, against what we're seeing in the data, we're pleased to see that our ropes are actually cleaner. We're getting less background events than we expected. So only about 27.5% what we expected, which is very nice. And we just checked, and this analysis seems to be very stable to NG threshold, which gives us good confidence that we're really seeing and understanding the ropes backgrounds now. Okay, so what can we do with these lower backgrounds that we've measured? Well, one analysis we're doing with the water phase data is a search for invisible nucleon decay. So if we have nucleons in a water detector, mostly oxygen 16, and if one of the nuclei in oxygen 16 were to decay into something we didn't see, something invisible like 3 neutrinos, we'd be left with an exciting state of oxygen 15. And that would then de-excite, emitting a gamma of 6 to 7 MeV. And in our very low background detector, it's very easy for us to see these 6 MeV gammas because they'll scatter electrons giving cherenkov light. So we're looking for this signal of the gamma from the nucleon decay. And in the absence of seeing it, we can place new limits on these decay modes. So we did this for the first water data set, and these are the limits we published in PhysRevD. And we're repeating this analysis on the new data set with more live time and these lower internal backgrounds, and also improved optical modeling. So now we understand our detector better. So these were the limits we had before. Blue just highlights the ones that are SNO plus limits. And these are our projections. So we see we'll improve by nearly an order of magnitude on most of these, we hope. So this is underway, and hopefully, again, watch this space. A note on, so we're running the water detector with this very low threshold now. It's running, it was running stably. So that meant we could actually detect neutrons in the water phase. So on this plot on the right here, I just have the simulated trigger efficiency for the detection. You can see above 8 PMT hits, we've got pretty much 100% efficiency. And comparing that to the signal you'd expect from 2.2 MeV gammas that you get when a neutron captures on a proton in water, you'll see that we should be able to see at least half this signal. And the reason why we want to see neutrons is because they're produced by inverse beta decay. So if an antineutrino comes into the detector and interacts on a proton, we get a neutron and a positron. So we see the positron in prompt light, and then after a short delay for the neutron to capture, we also see a 2.2 MeV gamma, which means that you've got a nice time coincident signal to tag these events. So we calibrated the neutron capture efficiency with an americium beryllium source, and we could tag the events by looking for the prompt events, which was a 4.4 MeV gamma, and then the delayed 2.2 MeV gamma. By plotting the time between them, we could see a very nice decay curve consistent with the capture time of the neutron. And we could use that to calibrate out our efficiency for seeing the neutrons. And under these conditions, it was about 50% across most of the detector volume. This is radius on the x-axis here, with this line being the acrylic vessel. And that was published in this PhysRevC paper. So that means with these very low backgrounds and high efficiency at low energy threshold, we've got an opportunity to look for reactor antineutrino events through inverse beta decay, which would be the first time this has been observed in a pure water detector. So we've got two analyses under development, one using log likelihood and one using a boosted decision tree. And both of these give you rejection between the neutron signal and accidental backgrounds, just because you get two backgrounds occurring in the same time window. And by cutting on these, you can reduce the accidental background by a factor of 10 to the 4, because actually there are a lot more accidentals than there are neutron signals, and we can retain 15% of the neutron signal. So with those criteria, we can expect to see about 2.5 signal events in our internal volume against about half a remaining accidental event. So still low statistics, but it's an interesting thing to pursue. Okay, so I've talked about the water. I'd like to now move on to the scintillator phase of SNO+. So as I talked about the water detector, let's talk about the features of a scintillator detector. So now, instead of a few hits per MeV, you get thousands of photos produced in scintillation light, which results in hundreds of PMT hits per MeV in the detector. And that means you can go down to a much lower energy threshold, so well below an MeV. And it's also actually easier to clean scintillator than it is water. So we can purify away more of the uranium and thorium because they've got more affinity to water than organic liquids. And scintillation light is isotropic. It's not directional like cherenkov light. So that is sort of a downside, but I've got more to mention on that later. So this plot on the right is actually summed over a few events just in the SNO+ event display, which shows that we're clearly seeing more light in the top half of the detector where we have scintillator than in the bottom half. So scintillator filling has been led by the SNOLAB team. We are filling the detector with purified linear alkyl benzene, or we call it LAB. And to that, we add 2 grams per litre of PPO. So PPO is a fluor that absorbs and re-emits the light to ensure that the LAB doesn't self-absorb and we get a good light yield out of it. So on the left here, I've got images of the purification and filling systems in the lab underground. So a feature of the experiment, and I guess of SNOLAB, is space is a constraint. Everything is down there. It's really squeezed in down there, and hopefully these pictures give you some idea of this, which is one of the challenges of getting this thing up and running. And on the right-hand side here, I've got some images of the rail cars that we use to transfer the scintillator from surface to underground. So here is a view of the purification and filling procedures. So we get our deliveries from the SEPSA plant in Quebec, and we fill up a storage tank on surface at the surface transfer facility. We ship that underground in these rail cars you saw an image of, and then we pop them in tanks underground. And then we have various steps in our scintillator purification plant to distill and extract and steam strip the backgrounds. And we will add our PPO to the mixture, and also at the late stage tellurium. I'll show you how that fits in afterwards before adding them to the detector. And the quality of the LAB that we put into the detector is very important, because in order to get this good light yield, it has to be very optically pure. And optically pure is also an indication that hopefully we're doing well on our other backgrounds as well. So we test the quality hourly during purification when the plant is running. We're filling the detector. And these plots are just some of the quality assurance plots that we extract. So there's a lot of work by a lot of people in the QA team from both SNO+ and SNOLAB to make sure that this is all going smoothly. On the left is a UV vis absorption spectrum, where absorption is on the y-axis, so the lower the better. And above 360, we see very good absorption from what's coming out of the plant. Below that, it jumps up steeply, but we're not worried because this is due to PPO. This is what we expect. So we just can't test down here once we've added the PPO to the LAB. The relative light yield we measure as well. And you can see here points that are from benchtop purified LAB, and then you can see what's coming out of the plant. And it's actually got an even better light yield than we expected from our standards. So we're really pleased with the quality of the scintillator that's been going into the detector. So we began filling in 2019. We did have some challenges to iron out at the beginning, but we were getting better and better at filling towards the end. And as things would happen, we were doing very well in the last week. We managed to get 75 tons into the detector in 1 week, and then we were hit by COVID. So we have stopped with 47% full detector, which equates to about 75 centimeters above the equator. I've shown this image here because I think you can actually see the line between the LAB and the water. It's actually very hard to see because the liquids are so optically pure. But we definitely have scintillator in the detector. And the good news is at least that the LAB deliveries have restarted at the end of July. So we're thinking about how we can move to get more scintillator in as soon as we're allowed. So with what we've got in the detector, well, as soon as we had a little bit of scintillator in the detector, actually we started characterizing it. And one of the first things we did was to measure the light yield. So we can put calibration sources in through guide tubes into the external water region so that they're outside the acrylic vessel, not in the scintillator, but the radiation gets inside so we can see it. And this is with an americium beryllium source shown here, the events in vertex position. And we calibrated the amount of light we were seeing per MeV with both the americium beryllium source and an N16, the nitrogen 16 source that I showed earlier. So we only have 0.5 grams per litre of PPO in the detector at the moment. We're aiming for 2 grams per litre for optimum light yield, but because of the way we were filling and some issues early on, we don't have the full concentration at the moment. But even with that, we're seeing about 300 PE per MeV, photon electrons per MeV. And if you extrapolate that to the full floor loading, we expect to see about 650 photoelectrons per MeV. And even at these lower light levels, we can start looking at the scintillator backgrounds in the detector. So what we really want to understand is how clean we've managed to purify it. We want to measure the intrinsic uranium and thorium levels in the scintillator. So for this, this is the uranium chain here, and we can use the fast time coincidence of the 214 bismuth polonium decays. So the decay time of this polonium is 164 microseconds, so it means it comes very quickly after the beta decay. So using a time coincidence, you can tag these clearly. And you can do the same with the thorium chain, but with bismuth 212, polonium 212. Now we do get some radon that comes into the detector while we're filling. This has a half-life of 3.8 days, and that does decay away. But really what we want to get at is the backgrounds below this decaying component, what's actually going to stay in there. So we did have some trouble with the background studies because the scintillator stratified a little bit and we were seeing different things on different days and at different levels in the detector. But the good news is, I guess, the silver lining of lockdown is that without touching things, the detector became very stable and the backgrounds became isotropic, so we could really get some good measurements. So I've focused here on the last 2 recent weeks of data when things have been looking stable, and we count up the number of tagged BIPO events per day, plot them against time, and you can clearly see that we're still seeing radon that's come in with the filling decaying away. But so we fit out this exponential plus a flat component, and it's that flat component we're interested in. So what's the residual amount of radioactivity? And we're currently fitting out about 5 times 10 to the minus 17 grams per gram of uranium in the detector. And doing a similar analysis for the 212 BIPOs and thorium, we get a very similar number, 6 times 10 to the minus 17 for that. And the good news is that both of these background levels, if we didn't manage to get them any lower or do anything else, they would be below the requirements for our neutrinos double beta decay analysis to go ahead, which we'll talk about later. So just to touch on it briefly, I said that you don't get any directional information from scintillation light because it's isotropic. However, because we're running with very low PPO concentrations, and that means the scintillation light yield is lower, and we have quite a slow rise time currently in the scintillator, which means that you might still see Cherenkov light, because when, say, a solar neutrino comes into the detector, produces your charged particle and an electron, that still produces Cherenkov light in scintillator. It's just that we get so many more hits from the scintillation that is mostly drowned out. But at this point, we think we've got a chance of seeing this prompt Cherenkov light. And using this Cherenkov light in order to get some directional information is a really holy grail for double beta decay experiments of this type, because solar backgrounds, I'll show later, are one of our major backgrounds. And we know where the sun is, so we know what direction they should be coming in. So we've got students who's working on a proof of principle to see if we can see the sun in this partial fill data, the direction of the sun. Okay, so what else can we do with Scintillator? So one of the things that we think would be very interesting to do with, as soon as we've got Scintillator in the detector, is to look at antineutrinos, reactor antineutrinos. So this plot is another plot I took from recent Neutrino 2020 talks, and it shows the solar preferred values of delta M 1,2 squared, and also those that come from the Camland experiment, which is actually a reactor experiment, or was a reactor experiment in Japan. And you see that there's some tension between the two best fit points. And if we plot these two different best fit points out in the spectrum we expect to see for reactor neutrinos at SNO+, so oscillated based on these parameters, then we see two very different spectra. And this is partly just because of the placement of the nuclear reactors with respect to where SNO+ is. And because we see very different spectra, we've got a good chance of separating out these two scenarios. So, and also, it would be nice to say that we can also measure the solar neutrinos from boron 8 down to about 2.8 MeV, we think, in this detector. So this plot shows sensitivity for two different scenarios. So if our data was at the best fit reactor parameters from Camland, or in red, the best fit solar parameters, and you'll see that plotting out the 90% confidence levels in terms of the oscillation parameter space, tan squared theta 1 2 on the x-axis and delta m squared 2 on the y-axis, you get very different contours out, which means you've got separation ability between these two different scenarios. So this is only with 1 year of pure scintillated data. But I should point out that this is a time coincidence analysis because reactor neutrinos interact through inverse beta decay. And because you're tagging the positron and then the neutron, you can easily identify this signal even with more backgrounds in the detector, like 2 neutrino from Tellurium. So once we've loaded Tellurium, we can still do this analysis. Likewise, if we're looking for antineutrinos, we can also do geoneutrinos. So this is actually the same plot, but now I've highlighted the lower end of the spectrum, where these curves here are for geoneutrinos from uranium in blue and thorium in red. And these are interesting because they tell us about physics inside the Earth. Radioactivity is responsible for a large fraction of the heat production in the Earth. And if we can measure these geoneutrinos, it'll be the first measurement of geoneutrinos in North America. So the only other experiments that measured so far are Camland in Japan, Boroxino in Italy. So we'd be really contributing to the global understanding of geoneutrinos through this measurement. And again, is an IBD signal, so we can continue this through the Tellurium phase data. One more thing we can do in Scintillator and also in Tellurium phase is look for supernovae. So if a supernova goes off in the galaxy, we actually get quite a rich signal in SNO+. This plot is probably too complicated to go into much detail here, but it shows the time of the run. We will see some inverse beta decay events, maybe an increase in these before a supernova. So we're thinking about having a pre-supernova warning. You get a sharp burst from neutronization and then the cooling of supernova, but note the x-axis here is 15 seconds. So supernovas are very sharp signal in time. So we obviously have to have a burst trigger to identify these. And then if a supernova at about 10 kiloparsecs did go off in SNO+, these are the number of expected events we think we would see. So as well as inverse beta decay and elastic scattering, we expect to see some proton scattering, which are very low energy. So depending on our energy threshold determines how many we would see, maybe 50 above 200 keV. But we also get some interesting signals from charge current events or neutral current events on carbon, which will be interesting too. So it's a very rich signal that would help us to understand supernova more if one went off while we're taking data. Okay. So I now want to spend the last portion of the talk talking about tellurium loading of the detector. So we've chosen tellurium as the 130 isotope of tellurium is a double beta decay candidate with a Q value of 2.5 MeV, and it makes up actually 34% of natural tellurium, which is a very high fraction for a double beta decay isotope. Remember at the front I said there's only 35 isotopes in nature known to double beta decay, and most of them need costly enrichment to get any any appreciable amount of the isotope into your detector. But tellurium is sort of the golden channel with this 34% natural abundance. And SNO+ have developed a method to load the tellurium into the LAB, into the liquid scintillator, and still maintain a good light yield. So that's the key thing that we needed to do. And for the initial phase of SNO+, we aim to load 0.5% natural tellurium by weight into the detector, which equates to 1,333 kilograms of the tellurium isotope. So how do we do it? Well, we use a compound called butanediol, and by mixing that with telluric acid, which is how we buy our tellurium to start with, we often call this T, telluric acid, we form an organic metallic compound by mixing these together. You can see here it releases some water in the process, and this tellurium butanediol is then, we can just mix it straight into the scintillator. We add some wavelength shifter bis MSB and also a stabilizer called DDA, which helps the cocktail to stay stable. And this cocktail is very transparent. And we predict about 460 hits per MeV for this 0.5% loading. And we've had many tests, many samples of this being created, and we've seen stability of this cocktail for over 3 years. I can show you one of those stability tests. This is one of the larger scale ones. We've got 100 litres in a tank at Boston University, which is observed by some PMTs to see cosmic rays going through this tank. This is the final cocktail we want to use in the detector, so all these components. And you can see that over time, after some initial setting up, the ADC count, so the measured light from this test tank, is really stable over time. And it's been running since March 2019, so that's well over a year. Okay, so here I'm showing you some images of what our plants actually look like underground, and also the plan images. So this is the purification plant, and this is the tellurium loading plant. And as I pointed out for the scintillator plant, the same features exist. They're squeezed into tiny spaces, very compact designs to fit into the space available in SNOLAB near the SNO+ detector. So the good news is that the construction and installation of the purification loading plants is finished. These two plants are going to aim for ton scale loading. We were preparing for the first test batch of tellurium purification and synthesis. Obviously that's on hold due to COVID, but we hope this will resume once we're back in the lab. And the purification we expect to achieve with these plants is of order 10 to the minus 13, 10 to the minus 14 for the uranium and thorium. So you notice it's not as low as the scintillator, but we've only got sub% level tellurium going in, so this is good. Okay, so let's look at the backgrounds, because to look for this Neutrinos double beta decay signal, the important thing is to really have a good understanding of a background distribution and have that to be as low as possible so we can see this rare decay signal. So we obviously have backgrounds that occur in the scintillator. The biggest of these is boronate solar neutrinos. We'll have backgrounds associated with the tellurium that we're adding. We also have backgrounds associated with the detector components that are already there and coming in from the outside. So I'll show you how these translate into what we think will be a problem for our Neutrinos double beta decay analysis. So we define a region of interest, which is just that energy region round the endpoint of the Neutrinos double beta decay. So we actually define this to be offset, so it goes from minus half sigma below the endpoint to 1.5 sigma above the endpoint, and that's due to the steeply falling 2 neutrino backgrounds. So if I take you around this pie chart, which is our background estimate for a year, which is less than 10 counts in this region, the boronate neutrinos are the biggest component, but at least these are well measured. We've seen them in previous experiments, but unfortunately we can't turn the sun off. The internal uranium chain, we reduce this obviously with the purification plant. We've already measured uranium at less than 10⁻16 in the partial fill, so at least we know that the LAB is pure enough to go ahead with this measurement. Same goes for the thorium, internal thorium decay chain. The externals, I told you earlier, we've measured these in the water phase, and we think that actually we're in a better state than this pie chart suggests. These reduced by about 23%. The 2 neutrino backgrounds, as I said, we've got this asymmetric region of interest for our signal, and this is sort of governed by our light yield. The more hits we have, the narrower our sigma is, and therefore the less backgrounds will be in it. And we're assuming 460 PMT hit per MeV, and all the signs from the cocktail test suggest that's about right. And then cosmogenics is a very small component here. Our telluric acid has been underground for several years now. We've purchased it all for the experiment. It's waiting to be purified and put into the detector. And the purification should give us another factor of 100 to 1,000 purification against these dangerous cosmogenics. Beyond that, so these are the backgrounds we expect. We can use the pure scintillator phase before we put the tellurium in to measure the background model without the tellurium components. And that allows us to test for any unexpected backgrounds, especially related to detector instrumental effects and things like that. And also we will stage the loading of the tellurium. We won't put it all in at once. And this allows us to assess the remaining tellurium backgrounds and to make sure they scale as we expect with the tellurium amounts. So I want to show you just a couple of analysis reaches for how we approach reducing the backgrounds in the data. So one is obviously these bipods, as we call them, the 214 and the 212 bismuth events, which have quite high Q values, so could contribute to the region of interest. But because of this time coincidence between the beta and the alpha, we can actually reject these with very good efficiency. So there's two different ways these events will contribute to our data, either as separate event triggers where the alpha is late enough in time after the beta that it will trigger the detector again, in which case we just reject events that are very close in time and consistent with the beta and then an alpha. And the other way is if the alpha actually occurs very fast after the beta and they occur in the same event window. And then we come up with classifications based on the distribution of the PMT hit times, because obviously this looks like 2 events instead of 1, but some of them are harder to decipher. And with these 2 analysis techniques, we think we can get 99.995% rejection of the 214 bipods, which is what we need to reduce these backgrounds. Another analysis that's been underway is to look at multisite rejection. So most radioactive decays give a beta and a gamma emission, whereas double beta decay is 2 electrons. So electrons don't travel very far at all in the scintillator. You can see in this plot of track length here, they're in this first bin, whereas gammas tend to travel up to, a meter or 2 to deposit their energy. And this means that we end up with multi-site energy deposits for most of the beta gamma backgrounds. And you can build a likelihood ratio statistic based on the PMT time residual again. And it shows that this is a powerful method to distinguish a number of the dangerous cosmogenic backgrounds from the double beta decay signal. So just from a slightly different timing spread. So what does the spectrum actually look like in our region of interest? So I said we define this region of interest in energy. That sits here. If we did have a 100 millielectron volt neutrino, the double beta decay signal would look like this. Oops, I've got ahead of myself. In the red, we have various background contributions. You'll see that the boronate in brown is the biggest. These colors are all the same as the pie chart I showed earlier. The external backgrounds are small, but they're a little bump here. But actually this plot I'm showing is just for a particular fiducial volume. And in this plot in the top right-hand corner, I show the counts of externals in black, or analytical signal in red, against the radius, again radius cubed, so it's normalized in volume, and you'll see that this is dropping sharply. So rather than just cutting in radius, if you use both energy and position or radius in the detector in your fit, then you can actually get a much better hold on these incoming backgrounds. Okay, so with this projected spectrum and a fairly simple analysis, we get a half-life sensitivity of just over 2 × 10⁻26 years. So that means that if we don't see any signal, we don't see this red bump here. And actually this is a big red bump that we could exclude. Then we can say that the double beta decay half-life is greater than this, and the neutrino double beta decay mass is less than between 37 and 89 millielectron volts. And this range is actually it's a theoretical uncertainty from the calculation of matrix elements that convert between the half-life and the neutrino mass. Okay, so I'm running out of time a little bit, so very quickly I can show you that we've been working on the likelihood analysis, improving this with the Markov chain minimizer, and including not only the energy and radius as observables, but also those multi-site discriminators I showed you. And we can show that we can get improvements on a half-life sensitivity, a very similar number actually for only 3 years of loading as opposed to the 5 I showed earlier. And this figure here just shows that the likelihood is quite powerful with these multi-site discriminators to help separate out any cosmogenics. If we have more in the background than we thought we did, we could identify whether we got cosmogenics or signal. So in the last few minutes, I'd just like to tell you a little bit about what we could do beyond this first phase with 0.5% loading of the tellurium, because we've done lots of R&D on the cocktail, and this plot on the right shows the percentage loading by mass. So 0.5 is here, but actually you can add in more scintillator and only get a slight reduction in the light yield. And we've shown that you can get up to 10% loading by weight of tellurium into the scintillator and still get an appreciable amount of light out of it. And improvements in the loading scheme have shown significant gains back in light yield. So our main background is still going to be the boron 8 solar neutrinos. That's not going to change depending on what's in the cocktail. But if we can improve this loading scheme and still keep a good light yield, we can significantly enhance our signal. And the incremental cost of adding more tellurium, given that you've already got the loading schemes and the plants and everything in place, is only $2 million per ton of tellurium, which is very cheap for a neutrinos double beta decay next generation experiment. So here in these two plots, there's some sensitivity, half-life sensitivity against the percentage loading. So the 90% confidence level that you put on it in the scheme where you reduce the uranium and thorium level. So this is the nominal level we're working with, but if you could reduce that, you'd also get a big win in sensitivity. And in this right-hand plot here, we just show sensitivity in a scenario where we run for a couple of years with 0.5% loading, and then we start adding more tellurium and ramp up our half-life sensitivity. So 2 additional additions of tellurium, and we could get to half-lives of 10 to the 27 years. So this plot tries to summarize our potential future sensitivity for double beta decay. The neutrino mass is on the y-axis. This is sort of, up here is where we are now. This is the inverted hierarchy region I showed you earlier on that lobster plot. And on the x-axis, we've got basically the physics sensitivities to seeing a signal, which is a combination of the half-life and the phase space, because when you compare different isotopes between the different experiments, so the different isotopes are given in different colors here, then without taking into account the phase space, it gets complicated. But we'll see the existing experiments are in the dark lines here, and we put the projections for future phases of SNO+ in the dotted line, showing that we think we can push down into this inverted hierarchy region with 2.5% loading. So that gets me to the end of what I wanted to say today. I'll just summarize and tell you hopefully I've shown you that we've got well understood detector from the water phase. We've seen the backgrounds are very low, and we've got all these physics analyses that are underway for the water phase or already produced. The detector is currently half full of scintillator, and we've been working hard to analyze that. So we've got an early understanding of the performance of the scintillator and the main backgrounds. And there's all these different physics we can do with the scintillator and the detector. I've talked about the Tellurium loading and purification systems and how they're progressing well for this first phase 0.5% loading. And hopefully I've shown you that there's huge potential in this method. So we maybe extend beyond this initial phase and really make big steps in sensitivity for double beta decay. And I'll leave you with this image of the collaboration, which incidentally was taken exactly 1 year ago. Happy times from a collaborator meeting at SNOLAB. Thank you very much.
Thank you a lot. Are there any questions? Thanks.
Thanks.
Sorry, it's very...
It's online, yes.
Are there any questions? Please raise your hand or just speak.
I have a question. I think it was regarding the floor, how your the floor is still quite low. You're only at a quarter, I think, of your amount that you're going to have at operation. But because of the low floor, you're able to get some cherenkov signal over the scintillation. And so that's giving you directionality of solar neutrinos, I think. How does that transition as you start increasing the amount of floor and
so as we increase the amount of floor, then we'll get a lot more light yield from the scintillator. We'll basically double the amount of scintillation light roughly, which will make it much harder. And also the timing gets faster. So the scintillation rise time you see here will be sharper, which is a good thing because it will give us better resolution in the scintillator phase. But it does mean that it will be really, really challenging to see this cherenkov. So a lot of people have tried this in scintillator detectors, and nobody's really been able to make it work in a detector optimized for as a scintillation detector. But maybe if you can prove it in this phase, then tweaking the scintillator for a future detector, there's a lot of people working on water-based liquid scintillators and slow scintillators, and there are various lines of research out there to try and look into this, because it's you know, this boronate background is big, so anything you can do to reduce it is really, really tempting.
Any other comments or questions? Can you show again the sensitivity with the uranium and thorium, 1/3 of the uranium and thorium, like I was 56, 57?
This one, yeah. Sorry, I should make it bigger again.
No, it's me that I have to be looking at the small one. The kink for the ear fourth is on the dotted line.
Yes.
No. Why?
I did ask myself
when you do the transition, then
earlier. I think
during the transition you go up. That's clear. And then at ear fourth, there is two different slope, or maybe it's just me. On the right plot.
On this. Oh, on this. Sorry. So on this side, so this one on the left is changing the uranium thorium levels and just the loading versus 5 years. But on the right, we're plotting against time. So this is assuming that after a couple of years, so 2.5 years, we start adding in another % by weight of tellurium.
Yeah, so I understand that the slope of the sensitivity.
Oh, you think there's another bit of a kink here? I think this is. Yeah, I think this is just to do with plotting. So obviously we wouldn't, you know, we wouldn't be measuring every day. We would collect a data set and then so I think this is just in making this plot, they've taken specific points to say, you know, what's our sensitivity now.
Okay.
Although I mean, I can check offline. That's.
No, I thought that because, I mean, if you continue with the first slope, it's nicer. Okay, sorry, thank you. Are there any jitter?
Yes, I wanted to say thank you. That was a lot of information. I don't think I could have pulled off trying to talk about half of that stuff. So I guess I had a couple questions. So when you were looking at your Bipod counts, you showed a plot of counts per day, and it looked like you're getting down to 20.
Yeah, let me go back.
And that's 20 over the 40% full detector?
So here, yeah. Oh, hold on, let me reduce you. Yeah, so this is just counts within a selected analysis region. So because in reality, when we do the double beta decay, we'll be cutting away from the acrylic vessel to get away from the external backgrounds. And we know that we have backgrounds that are getting in from the water phase. So we want to stay away from this interface as well. So we've got some quite tight analysis cuts on this. So sorry, there isn't a normalization on these counts per day. It's really for the trend over time. But that
those
is
cuts
the selection here, yeah.
So I mean, it seems like a good chunk of the detector. Is this getting low enough that you can start to measure other backgrounds? You know, things like krypton, I guess, and maybe I guess that goes to. Do you think you'll be able to produce a spectrum and measure things like the 210s and?
Yeah, so we can see the 210s. We're looking at them now, and we've got people working. You know, each of these backgrounds. I think the krypton. Potassium 40, carbon 14. We've got students working on each of these, often 2 people per background. So yeah, we're pushing on it. We're not, I think, I can't say that we've seen anything for the krypton yet, but yeah, it has been a challenge in the early days with the radon, but we are really getting to the point where these backgrounds are low enough that we can really seriously do these other analyses. So I can't say anything definitive on them yet, but yeah, we're trying.
And then I guess the last one on the backgrounds, what do you expect from the metal loading of the detector affecting the uranium and thorium contents?
So that will depend on how well the purification plants work. From the test runs of the tellurium purification, we've seen that we can achieve the purification levels that we want in terms of uranium and thorium, and projecting the fact that we're adding 0.5% loading, we're sticking with these numbers in the pie chart, I guess, in terms of that is our best guess of where we'll be in terms of the complete cocktail backgrounds. So the tellurium does contribute more than the LAB, but the plant should do its thing in terms of purifying that.
Thank you.
Are there any other questions and comments? If not, since we are on top of the hour, I would like to, no, okay. Ben just started. I would like to thank you very much. Very nice talk. And I would like to remind every